So we're talking about multiple alignment. Actually, we're talking about progressive multiple alignment. It's a particular type of multiple alignment. This is often sometimes called iterative pairwise alignment or something of that sort as well. But at any rate, what I stopped with last time was the following. We had a definition. S is a set of strings. And T is a tree. I think I said there were K strings. T is a tree with exactly K nodes. Node is another word for point. So last time I might have been saying points, but node is another word for point. And each labeled with a distinct, that means different, string in S. Okay, so I'll finish this definition in a minute, but I want to remind you of the example that we had. So here was AXZ, and I'm going to refer to this as sequence 1. And here we had another AXZ. They happen to be the same, but that's identical, but we'll refer to it as a different sequence. And here was an AXXZ, and here was an AYZ, and here was AYXXZ. Okay, so we have a set of K strings. In this case, K is 5. T is a tree. There's our tree with K nodes. 1, 2, 3, 4, 5 nodes, each labeled with a distinct string in S. Okay, so here's that labeling. And then we say that then a multiple alignment M of S, a multiple alignment of those strings is consistent with T if what? If the induced pairwise alignment of SI and SJ. These are two strings. I'm subscripting one with an I and one with a J. Okay? Alignment of SI, SJ, which are neighbors in T, if that induced alignment is an optimal pairwise alignment, for S1 and S2, SI and SJ, sorry. Okay, there's a lot of words. We're going to take some time to unwrap this and look at the example and then explain why this is really important. This is the key to a great deal of algorithms. Many algorithms for multiple alignment are based on this definition and a theorem that will come from it in a minute. So here we have the tree, which labels where all the nodes, each node is labeled with one of the sequences from our set S, and these sequences are all distinct. I mean, these are actually identical, but this is from sequence 1, this is sequence 2, and so on. Now let's look at this part. A multiple alignment is consistent with T if the induced pairwise alignment of two sequences which are neighbors in T, if that induced pairwise alignment is an optimal pairwise alignment for Si and Sj. Okay? So let me give you the same alignment we had before. Ax x dash z, Ax dash dash z. Now this is sequence 3. This is 1, 2, A dash x dash z. 4 is A y dash dash z. And 5 is AY XXZ. Okay. What are the neighbors? The neighbors are, for example, 1 and 3. All right? When you look at the induced alignment, remember, induced means the alignment that comes from this multiple alignment. So here we have a multiple alignment M, and for any pair of sequences, we can look at it, and M gives us an induced alignment. It aligns, for example, 1 and 3, just as we've shown here. They're next to each other, so it's easy to see it. But if we were talking about, let's say, 3 and 2, all you have to do is still just take your two fingers and go along like that and see what the induced alignment is. Okay? Now, if I look at every neighbor pair, 1 and 3, for example, this induced alignment is as good as you would get if you were just trying to find the optimal alignment of these two. Space against space is counted as a 0, so essentially you can ignore that. If I just told you these two sequences and asked you to find the best alignment by similarity measure, there's no alignment of these two that's any better than that. All right? And similarly, if I look at 2 and 3, 2 and 3, 2 and 3, sorry. 2 and 3 are these, okay? Then, again, there's no better alignment than what you see induced here. Even if you were only asking about 2 and 3 alone, separate from a multiple alignment. And if you look at all the neighbors, 4 and 5, again, it has that pairwise optimality criteria. Pairwise optimality, what's the word I'm looking for? Anyway, it's pairwise optimal. The induced alignment here of 4 and 5 is as good as you would get even if you just looked at 4 or 5 in isolation, just by themselves. And the same thing with 3 and 4. 3 and 4, these are far apart, but you have one match, one mismatch, and another match, another space. And that's, if you just think about these two sequences alone, AYZ and AXXZ, that's as good as it gets. But it's not true for every pair. Can anybody see a pair up here where the induced alignment from M is not as good as you would get if you're just looking at that pair by themselves? Which one? 2, 4. So 2, 4 is AXZ. If I was just looking at those alone, AXZ and AYZ, that's the best pairwise alignment you could get. But the induced alignment here of AXZ, 2 and 4, and AYZ, it has one match, two matches and two spaces. So that's not as good as this one, which has two matches and one mismatch. We're just counting matches, mismatches, and spaces, okay? Not putting particular values on them. So consistency says that the pairs that are neighbors in this tree, their induced pairwise alignment is as good as you would get even if you looked at those pairs in total isolation. it doesn't require that it's true for pairs that are not neighbors, such as we just looked at, AXZ, which is 2 and 4. Okay? All right. Now, the following, well, let me ask you the following thing. We're trying to get a good multiple alignment under the sum of pairs criteria. Sum of pairs says when you have an alignment, a multiple alignment, I'm going to evaluate how good it is by looking at each pair and looking at the induced alignment of that pair. So is it good or a bad thing when a pair, the induced alignment in the pair is as good as you could get from that pair in isolation? Is that something you want to have or you don't want to have? Should I flip a coin or what?
Will you repeat your question?
Okay, I'll repeat the question. The criteria we're trying, our goal is this. Find a multiple alignment we're doing maximization. The notes talk about minimization, but let me just, well, okay, I want to back up. I mean, if I'm going to make this really formal, let me put in a new definition that we haven't made before. For two sequences, SI and SJ, Dij equals the minimum number of mismatches plus number of spaces in any alignment of SI and SJ. Okay? So previously when we were talking about aligning two sequences, we were talking about value, and that was number of matches, that's good, minus the number of mismatches, minus the number of spaces. And you want to make that big. A lot of people instead just talk about this value, or this Dij, which they call a distance, which is number of mismatches plus the number of spaces. And before, we wanted to maximize matches minus mismatches minus spaces. So intuitively, what we want to do here over all the possible alignments is minimize the number of mismatches plus the number of spaces. If you think about it, we're really getting at the same things, this distances versus the values. Okay? We're just not explicitly counting the number of matches anymore. All right? But these notes that I gave you are in terms of these D values, these distances, so I should define it. Okay. Then I'm going to define dm ij is equal to the number of mismatches plus number of spaces in the induced alignment of SI and SJ in M. M is a multiple alignment. Okay? So before I go on and before I restate the question, let's go back to this example to talk about what are the dm values. So what is dm of 1, 3? I've heard 2, I hear 1, I hear silence. Which one's right? 1 is right. Okay. So dm of 1, 3 equals 1. Because if you look at this, there's one space. These are counted as zeros, and this is a match. Okay. So let me just give you another example. These 2. Okay. So that's 1. That's also a 1. And these 2 is 1, 2. Okay? So dm of 3, 4 equals 2, right? 3, 4. 1 mismatch, 1 space. Does everybody get intuitively that a small d value and a large v value are pretty much telling you the same thing? Small d values say these 2 sequences are quite similar. Large v value says they're quite similar. Small v value says they're quite different or different. Large d value says they're different. Okay? And if you really think about it carefully, you can come up with a formula that's based on the lengths of the 2 sequences that relates a d value to a v value. Okay? So think about that if you like. All right, so now we know what dm is. Okay? So our objective is find a multiple alignment M of the sequences that are given to us to minimize the summation I less than j dm ij. This is the sum of pairs objective. Okay? This is the induced distance in the multiple alignment M of sequence Si and sequence Sj. We're summing these for all I less than j, so that means we're summing them for all pairs. Okay? I could make this less than or equal to 1, less than or equal to k to be absolutely explicit. But, okay, so for every pair ij, you're getting the dm value, and you're summing that up. And we're trying to make that small. We're trying to find a multiple alignment that makes that as small as possible. So we could go back over to the example and ask what's the sum of pairs value, but that's 5 times 4 divided by 2. 10 different values we'd have to find. 10 different induced values here, and we would sum up those 10 different induced values, and that's what the value or the total distance of this particular multiple alignment is. Okay? Yeah?
I just want to make sure, why does AXZ has 2 forms? 2 different...
AXE, just in this particular example, we're given multiple sequences. 2 of them happen to be identical. That's all. I mean, you took the protein the sequence from some gene or from mice, rats, giraffes, and whatever, and it turned out that the sequence for mice and rats were the same.
Yeah, but why they have different alignments? Like, when do they align X? Put X and...
Oh, why did these end up being aligned differently?
Yeah.
Just in the example. It's just an example. Okay. All right. All right. So we're trying to find a multiple alignment that minimizes this thing. Okay? All right. I'm not quite yet back to my question. I mean, we've had this question, but since people were confused by it, now I'm going back and making all these things very formal so we can formally state the question. But I'm not there yet. So let me ask a sub-question. What can people say about this? dm ij and dij. What relationship do you know between these two? Just based on the definition. Yeah. Okay. So that was for the front row. What about the second row? Or the back row? You probably didn't hear the answer. So, what do we know about the relationship of these two? Just based on the definition. Yeah, but the front row already answered. All right. This thing's got to be greater than or equal. Okay? This is the minimum possible distance when I just give you Si and Sj in total isolation and say do the best you can. Over any possible way you want to align it, this is the best one, the best value that or the best distance that you can come out, the smallest distance that you can come out. This is the distance that comes from a particular alignment. It's an alignment that's pulled out or induced from a multiple alignment. But it is nonetheless a pairwise alignment, so its distance has got to be greater than or equal to the best over when you're permitted to do anything you like. Okay? So always this is true. All right. Well, now what about this then? I will erase this. Now what do we know about this relationship? Okay, somebody towards the back want to offer an answer? Well, if it's true for the trees, it must be true for the forest. Right? I mean, each individual term here, this is greater than or equal to this. So when you sum them up, they better be greater than or equal. Okay? All right. We're trying to minimize this sum. We're equivalently minimize this sum. Trying to make this as small as possible over all possible multiple alignments. Okay? So is it a good or bad thing when you have a multiple alignment where dmij equals dij? Good or bad? Good. Somebody said, yes, right. That's what we're trying to do. We would like to have a multiple alignment in which every dmij equals dij. That's the best you can possibly do pairwise. So if it happens to be what you get out of the induced alignment, that's great. Okay? So in fact, I'm going to put this into my definition of consistency. If the induced pairwise alignment, which are neighbors, is an optimal pairwise alignment, in other words, that means that dmij equals dij. Okay? So actually, all I have now is all these definitions. Okay, I haven't really told you anything about what we can or can't do. But we have this definition of consistency. And we actually have an example here of consistency. This is an example where this multiple alignment is consistent with this tree. Because if you check out each one of the neighbors, you have dmij equal to dij. In each one of those 5 cases, or actually 1, 2, 3, 4 cases. All right? Okay, so two theorems I want to tell you about. So this is a theorem. for any set of sequences that you have, and any tree T that you use, and you label each node with a sequence, where each node of T is labeled with a distinct string in S. So no matter what sequences you give me, and no matter what tree you give me, and no matter what the way you assign the labels, okay, there is a multiple alignment of S, which is consistent with T. There is a way of getting the multiple alignment so that at least all the pairs that are neighbors in the tree, their induced distance is equal to their optimal distance. So dmij equals dij. All right? So that's the first theorem. I'll state the second one. And I actually want to try to prove this to you because it really is at the heart of progressive alignment algorithms. And it's certainly what's going on in the star algorithm. Okay? But how many people are having trouble parsing this? What this is asserting? Who's brave enough to admit it? Okay? So we have the definition of consistency. We have a restatement over there of what our objective function is, what we're trying to do here. And therefore, that suggests why we want dmij's to be equal to dij's. If we can get a lot of dmij's equal to dij's, that's going to be good. It's going to push down the induced alignment distances. Okay? And then I have this theorem here which says that, yes, you can get a certain number of these, a certain number of the dmij's to be equal to dij's. Okay? So, all right. I see a lot of blank stares, though. Can anybody formulate a question of what's bothering you? Yeah.
The question is that how to define the T. For a given T, then we can find the optimal consistent with that T.
Right.
How to define the T? I think there are many trees. So
Yeah.
how could we pick a tree that gives us the best alignment?
Yeah, but that's the next step. You're going ahead. The question was, how do we pick a good T? But the theorem just says, if I give you an S and I give you a T, then we can get a consistency. I want people to understand that first, and then we can ask the question of what is a good T, and how do people find it in the various multiple alignment methods. But right now, no matter what T is, this is a theorem. But I want people to be able to understand what's being asserted here, even if you don't see the proof of that yet. Anybody else formulate a question about what's being asserted? Consistent. Okay. A multiple alignment, this M represents the multiple alignment of these sequences S, is consistent with a tree T. And T, remember, is decorated with the sequences in S. So each sequence in S labels a single node in the tree T. But the multiple alignment is consistent with that tree if the induced pairwise alignment of an Si and Sj, which are neighbors in T, is an optimal pairwise alignment. So in other words, dmij, that's the induced distance in M, is equal to the best you could possibly do for ij in isolation. Okay? Well, that's the definition of consistency, and this was an example of consistency, and here was why it would be a good thing to have many pairs ij where dmij equals dij. It would be good to have that because this is the criteria we're using to gauge whether a particular multiple alignment is good or bad. This is the best you could possibly do, even if certainly you cannot do any better than this. And the more you can make individual dm values equal to d values, the closer you can get to making the sum equal to that sum. Okay, yeah?
So can we always find alignment that dn equals d? Or is it possible that we cannot find it?
Okay, is it always possible to make this sum over all ij equal to this sum over all ij? And the answer is definitely not. It's not always possible to do that. But what the theorem says is it's always possible to make the equality for certain pairs. Okay? For some subset of pairs. Okay, so this is, there is a multiple alignment which is consistent with T. That means that certain pairs, the pairs that are neighbors in this tree, those will have equal dm and d values. But the ones that are not pairs, they might not be equal. And in this example, they are not equal, not all equal. Some that are unequal. Okay? All right, but anyway, let's try to give a proof of this theorem. And the proof is constructive. It says I'm going to show you how to create a multiple alignment constructively, basically give you an algorithm. And I'm going to do it with this example. But, so I'm not going to write down formal abstract rules. I'm just going to do it with this example. And I think you'll get the idea just from seeing this one example. Yeah?
The definition of tree.
Right.
So basically you can connect any two nodes with a line.
You permitted to, but in the end you have no cycles. I mean, I don't want to have another line like that as well.
But it's allowed.
That would be a different tree, yes. Yeah. And this is for any tree. This theorem says for any tree you like. Okay? All right. So the way I'm going to do this, the way I'm going to build up this multiple alignment is I'm going to take a pair that are neighbors. And it's convenient to work from the outside in. Although I could do it differently. But so I'm going to take a pair that are neighbors, and one of them is on the outside of the tree so far. So I'm going to then find an optimal pairwise alignment, AXZ and AXXZ. That's an optimal pairwise alignment of 1 and 3. Right? Can't do any better than that alignment for those two strings. Remember what I'm trying to do. I'm trying to get a multiple alignment where for every pair that are neighbors, the induced alignment in the multiple alignment is as good as the pairwise alignment, the best pairwise alignment for them. Now, so far, I've achieved that. I mean, the first two ones that I did explicitly by doing the best pairwise alignment possible. So I certainly have achieved that so far. If I can keep this relationship between the characters in here, no matter as I expand, as I change the multiple alignment, if I can keep A against A, X against X, this X against the space, and Z against Z, then I will have achieved that the induced alignment of these two sequences in M is as good as the pairwise alignment of these two sequences by themselves in isolation. So the next thing I do is take another sequence that's on the outside, and it's connected now. It's neighboring something which is already here in my alignment that I'm going to build. So let's look off to the side. What's the best pairwise alignment of these two sequences? It's AXZ and AXXZ. Okay? Well, the old one that was already in there, among these two, whenever I do an alignment from now on, one of those two sequences is already going to be in here. Okay? My pairwise alignment between these two did not add any spaces in AXXZ. So what I do over here is I write this A under where this A is, this X under where that X is. Okay? And there's a space where that one was, and a Z. So what you see what I've done is I've just transferred this alignment, this pairwise alignment, into here. And because in this particular case, I didn't even add any new spaces in here, of course I didn't change the relationship of sequence 1 and 3. I got the best you can get from 2 and 3, and I didn't change anything about 1 and 3. So far, I've kept my assertion that the pairs that are neighbors, their induced alignment is equal to their best pairwise alignment. Okay, let's continue. I hope I actually get something more interesting here in a minute. Let's do 3 and 4. Okay. Oh, I said I was going to move one from the outside, but actually what I want to do is always something that's not yet in here with something that is in here. It's neighbor. It always has a neighbor which is in there. Okay. So let's do that alignment. What's the best pairwise alignment you can get there? Is AXXZ. Not very interesting. AY space Z. Okay? I hope this gets more interesting.
Can you do the other around A space Y C?
Yes, sure. That's just a tie. It's not going to change anything. So that's just a different pairwise alignment that's equally good. Okay, and it won't matter which one you use. But again, you see what happened is the old one didn't get any new spaces. So we can certainly add this thing into our multiple alignment without changing this at all, and therefore without changing its relationship or any of those relationships. So we get this A against that A, this space against that X, this Y against that X, and Z against Z. Now, this algorithm doesn't get interesting until I put some spaces in an old sequence. Okay, so hopefully we'll get there in this next step, because that's the end of this example. Now, what's left is the alignment of these two. What's the best? Good, we get some spaces. What's the best alignment of 4 and 5? It's AY space Z against AY XXZ, right? That's the best you can do pairwise. This is the old timer, okay? AY space Z. Now there's some spaces in there. I want this relationship, I want to add this one in to this multiple alignment M with this pairwise relationship without changing the pairwise relationship of any pairs we've already put in there. How do I do that?
It makes difference for if you write A space Y Z or A Y space Z. Now it makes difference. For the alignment 4, you first write a
Yeah.
circle 1.
Well, the algorithm is whatever the algorithm is. We may give a slightly different answer which way I did the pairwise alignment, but we're just going to run the algorithm. But my question is this: how do I put this new relationship in here without changing any of the other previous relationships, pairwise relationships? Yeah, I have to, because this has new spaces, A, Y, Z, Z. What I have to do is, in my old copy, I have to add in this case, one more space to make this line look like this line. Okay? Well, I think one space should be enough.
If Y is before the space, then Y is enough. But now the space is before Y, so we need 2 spaces after Y.
Well, let me just try it with one new space. Okay? And then tell me if I didn't do it right. Okay. So what does that mean? It means I want to do this. I break open a new column here. I put a space. Oh, I'm sorry. You're absolutely right. I see what your point was. This space came before the Y, whereas this space has come after the Y. Yeah, okay. So I have to add the new spaces here because I have to put the spaces in that came from this line. Yeah, 2 new spaces. If the space, yeah. Okay, so, and that's actually easier to do because I can just erase all these Z's for a moment. Space, space, Z's. And so what I'm going to do, I broke open the old line here where I needed to put in the new spaces. And I put in those spaces, I broke it open everywhere above it, everywhere that's in the existing M. I just make a whole bunch of spaces, opposite spaces, and those cost for nothing anyway. Those cost nothing anyway. And then I can put the A against the A, the Y against the Y, okay, but this is a space, and then the X, X, Z. And you see my point is that as an induced alignment here of these 2 sequences, it's got the same distance as this induced alignment. It's got some ugly spaces against spaces, but that's cost 0 anyway. All right? So basically the rule is any spaces you put into the old sequence from this pairwise alignment, you put them in to where that old sequence was, and you put it in everything else that's already in that M. And every space that was in the old sequence in M, you put that into the new sequence that goes into the multiple alignment. And then you make sure to line up the characters of these 2 in here the same way they were lined up in here. And what you get out of that is this induced alignment is the same as this optimal alignment. And the previous relationships, pairwise relationships, are the same as they were. And so if you had certain pairs being optimal, if their dm value equals their d value, previously, they will continue to have that. And when I've done everything, then I have M consistent with T. Okay? So that's my constructive proof of this. Now, it's in the notes. All right. Next is what is going on in star is this. star.pl. The tree looks like this. Okay, for k sequences, k strings, it's going to have k minus 1 nodes on the outside. Okay? And the only issue is what's at the center. Okay? The center sequence is the sequence SI, which minimizes the summation dij. Okay? For j not equal to I. So, if you compute first the distance between every pair of sequences, and how many people have played with star by now, by the way? One person? Two people? Okay, at the beginning of the star computation, it's computing the pairwise distances. It takes a little while. You give it 5 sequences, it'll compute 5 times 4 divided by 10 pairwise distances. And it prints out each distance. Then, if it finds the sequence I, whose sum of distances to everybody else is the smallest. Okay, it's kind of like a representative sequence. It's sometimes called a median sequence or a central sequence. It's a sequence whose sum of distances to everybody else is the smallest over all possible sum of distances from a single sequence. It's, in a sense, a good average reflection of the whole set of distances. And so that's what's being put here in the middle. And what's being put around here is everybody else. And then star.pl builds an M, a multiple alignment, which is consistent with that star, with that particular tree. Okay? And then it computes a measure of how good it did, which is dmij I less than j divided by summation dij. This is the best possible you could hope for in the numerator, in the denominator. This is what is actually obtained. Okay? It's not clear that you can ever do as good as this, but you can certainly never do better. This is what you actually get. Okay? And it computes that. Now, those of you who have actually executed this, what kind of ratios are you getting? Do you remember? 1.0. Yeah, they're small. You're getting like 1.0037 whatever. And there's an actual theorem, which is this ratio, if you use this star, this ratio is always less than, I think it's something like 2 minus 2 over k. 2 minus 2 over k. All right? Yeah. K is the number of sequences. Okay? Less than or equal to that. All right, so I'll continue next time, but when you play with star, realize what's the importance of this ratio that's computing, and that there's this theorem which says you're not going to get too weird. Things don't get too far away from the best you could possibly have.